So, we will continue with the printed wiring board technologies. This is the 7th hour in this particular module, where we are discussing the basic printed wiring board technologies. Remember, I have used the term system. So, this is a module that we have exhaustively looked at in terms of how a printed wiring board can be used as a system level entity. Now, we have also gone into the various sequence steps for plated through hole process as part of the double sided and multi-layer buildup. So, we will continue with the plated through hole sequence. What do you mean by a plated through hole? There is a dielectric material and then you have the copper at the top and at the bottom. Now, we are drilling a mechanical hole. These holes are meant for providing interconnects, electrical contact between the top copper and the bottom copper. When you drill a hole, the inside of the hole wall is a dielectric material, it is non-conductive. So, you have to make it conductive. So, the plated through hole process sequence will let you know how a conductive hole wall is established from using a combination of electroless copper and electroplating copper. So, we look at the sequence once again, and this is highlighted through videos. Now, if you look at the first step, as we have discussed last time, it is the image transfer process. So, I let you watch the image transfer, because this is going to be a very important step, whether we are going to do a pattern plating or a panel plating for a double sided printed wiring board. You can see here the board has been laminated with the dry film photoresist material. Now, remember all the properties that are required to be established before a dry film operation. The suitable masks for imaging the electrical layers are subsequently taken. They are aligned with the through holes that you have drilled, and then they are introduced into the UV exposure unit. You can see this is a UV exposure unit, where sufficient UV light is exposed to the dry film through the mask. Now, this will help establish an image. Now, this image is further stabilized by the developing process. So, the resist will be removed in the unwanted areas, and the resist will remain on the substrate where the circuit is to be protected, or in some cases where the circuit pattern requires additional copper to be added in terms of increasing the thickness of copper on the circuit areas. Now, this is the first step, that is the image transfer. Now, we get into the second step of the plated through hole sequence, which is called the electroless copper plating. So, once again I emphasize, we are not using an external DC current here. We are using a chemical reduction process from a copper rich solution and using some reducing agents to deposit copper onto the surface of the board as well as the through holes. Now, before that, if you look at the video, what we are basically doing is a micro etch. This will remove some amount of copper from the surface of the board to the extent of about 1 to 2 microns. This will provide more roughness, more surface area for the imaging process to happen in a good manner. Then the next step after the micro etch is a water rinse. Typically, you can use a cascade rinse or a spray rinse in some cases, as you have seen here, for 30 seconds. Then it undergoes an acid treatment in a 10% sulfuric acid dip to activate the surface with the acid. Then it is neutralized with water. So, these are all the cleaning processes. What you are seeing is basically a micro etch is a cleaning process, the sulfuric acid is a cleaning process to remove oxides and other debris that may be on the surface. Now, we are introducing into a pre-dip. Remember, the next step is going to be a catalyst activator, which is chloride base. So, we now wet the board with a chloride, hydrochloric acid. Now, it is introduced into a tray containing palladium chloride, which is our catalyst. You remember the equation that I have put up in the last class, where we described how the palladium is absorbed on the surface of the copper, and then to the surface of palladium your copper gets attached. It is a strong physical bond, and this again is very key to the reliability of the entire board. Now, after the recommended time in the catalyst, the board is now washed well, water rinsed for about 30 seconds. Remember, the water that we use here is deionized water, which is free from all contamination like chlorides, carbonates and so on. Now, the board is introduced into a post activator. You remember, the post activator will actually break the embryo containing the palladium colloidal gel into the individual palladium atoms, and they will be evenly distributed on the surface of copper as well as the hole walls. So, these are key processes in the manufacturing sequence. It could be a 8-layer multi-layer board or a 16-layer multi-layer board. They have to undergo these critical process steps. Now comes the water rinse after the post activator. Now, the board is ready for activation in the electroless copper bath. If you recollect, this is the electroless copper bath, the blue solution, which basically contains a copper rich aqueous solution, and at the time of usage, the reducing agent like a sodium hypophosphite or a hydrazine based reducing agent can be added. There are several reducing agents that can be used based on the recommendation of the manufacturer of the catalyst, because there has to be some compatibility. Now, you can see that the board is plated with copper. This is real nascent copper. It can get oxidized. So, the subsequent process has to be immediately carried out. Otherwise, you have to protect the copper with some kind of a anti-tarnish solution or a coating. Now, the next step in the PTH sequence is the panel plating process, which means the copper panel or the laminate, the entire panel gets plated, whereas in the pattern plating, as the name indicates, you will specifically open up those areas to receive plating. Now, in the plating process, what you are seeing here is basically a jig is attached to the panel for easy handling, and for the copper plating bath, as you know, there is an electrolyte, there is an anode and the cathode. Your PCB acts as the cathode. Okay. Now, here you see that the technician is now introducing the jig containing the panel, the printed wiring board, which is the cathode, into the copper bath, copper plating bath, and then the current density of about 20 amperes per square feet is now activated for the plating bath. So, you have two anodes on either side, here as well as here. You have the anodes in a bag, so that you get high purity anode getting into the electrolyte. Now, after sufficient time, here in copper plating, you have to calculate the area to be plated. There should be constant agitation, there should be good air circulation, and the distance between the anode and the cathode has to be measured, and accordingly you have to set the current density. Typical guidelines is 20 amperes per square feet, and it depends on what thickness you want to plate. Your final thickness, if it is around 32 microns or 35 microns, accordingly based on the, you can see that this panel is very shiny, a good coverage of copper has taken place on the entire surface of the panel, and if you go deeply and carefully into the microscope at this stage to look into the through holes, they will be well plated. You can see from a side shot here that the holes are well plated with the pure copper. Now, again this is going to be a key step. As the name indicates, in panel plating the entire board is plated. Now, you can do an image transfer on the printed wiring board and then remove the unwanted copper. So, you are now going to protect the areas that you require and then leave out the other areas for etching. Now, we will go into pattern plating. So, here the difference is that you will, after the electrolysis process, do image transfer onto the panel and then mask the areas that do not require additional copper plating. So, for this particular step, you do a acid cleaning first, because the copper that is going to be plated on the circuit areas, the base area needs to be clean for good addition of electro copper. Now, you can see here in this particular shot that the image transfer has been done by means of a photoresist material. Here the blue material that you see here is a photoresist material that has to withstand all the chemical reactions in the plated through hole line, and in some cases, as we have seen earlier, they also act as a etch resist. Now, during the plated through hole process sequence, you cannot ignore any step which includes a water rinse or an acid cleaning or a micro etch process, as the process step indicates, because if you miss out one of the steps or ignore one of the steps, you are going to contaminate one chemical into another tank, and then you will have lot of process variations, and that will affect the final yield. You can see here now that the exposed copper which is going to receive plating is micro etched for about 60 seconds using ammonium persulfate micro etchant. This is basically again to improve the adhesion and to make sure that the electroplated copper adheres well to the pattern area. The dry film, as I said, is going to protect the non-circuit areas from receiving copper. Also, we can see in this particular shot that the panels have a bus bar around the sides, that is basically for the jigs to hold the panel and also to receive the current from your jig through the jig, so that plating or deposition can take place at a uniform rate. Another aspect that you have to see here is, as we watch this video, this is the electrolyte, this is the acid copper bath. Typical timings are indicated here, about 30 to 40 minutes for 20 amps per square feet, you will get about 20 microns deposited. Again, you see here, after every process there is a water rinse to avoid contamination. Now, this area that is given around the panel is basically for the jig to be held and to provide even plating. You have to make sure that your electroplating bath provides even plating from end to end along the entire panel. If there is uneven plating, then you will have electrical issues finally, because it is not a complete translation of the electrical design. Now, there is a 10% sulfuric acid dip for about a minute or so, and then it is this copper that is plated exclusively on the pattern areas is now further protected using a acid tin pattern plating, using an acid tin plating bath, which contains a tin rich source, and then typically the current density about 20 amperes per square feet for about 20 minutes. Here essentially we are immediately protecting the copper from atmospheric oxidation by tin plating. You can see here that the entire pattern areas as well as the side bar areas are plated with tin. Now, the tin can act as a etch resist in this case. You can see now that there is a tin plated area, and on the contrast you see the dry film area which has protected the non-circuit areas so far. So, you have now seen what is a pattern plating and a panel plating. Now, we go into the final step of the PTH sequence, which is basically removing the dry film as well as performing the etching operation. So, the panels are introduced into alkaline sodium hydroxide caustic solution, typically about 5 to 10% of hydroxide solution, and you can see that the dry film is lifted off. It is basically stripped off the panel, and what you see here is basically the pattern areas which are protected with tin or plated with tin, and then you will see here the brown areas which are the copper, which is going to be removed by the next step, which is etching. So, the next step is basically in this case conveyorized alkaline etching using alkaline ammonia. We have seen earlier the different types of etchants. Alkaline ammonia basically contains ammonium hydroxide, ammonium chloride and liquor ammonia, in addition to copper as a catalyst to start with. You can see that there are spray nozzles from the top as well as from the bottom going through a conveyorized machine, and you can see here there is a water rinse at the end of the conveyorized line. In some cases, as you can see in this particular example, that after the first pass the board is not completely etched. You have to set the right temperature. There has to be complete control of the elements in the alkaline etching bath, and now the board is reintroduced into the conveyorized etching machine further to remove the existing copper. So, in some cases if it is a long line and if it is a large voluminous tank, then you can probably complete the etching process in one go or one pass, but being a prototype, this is now happening in the second pass, and you can see here that the board is completely etched out. You can see the base laminate and you can see the copper pattern areas which are intact. So, have a microscopic examination at this particular point to see if the etching process has been completed thoroughly without any undercut. Okay. That is a very crucial examination, quality examination that one needs to do. Now, the particular board has been solder masked. You can use a dry film or a liquid solder mask and then complete the operation, and you can also see that legend printing has been done. On the right side you can see legend print using white inks have been marked. So, this completes basically the plated through hole process sequence for doing a double sided electrical interconnection. Now, you can repeat these steps for a multi-layer board, but at the same time you have to look at final measured thickness. Therefore, you will use thin laminates for inner layers. Now, what are the post operations that one does after the board is completed? Quality inspection is a must at all stages. So, I would mark this as very important, because in the volume manufacturing you have to inspect the board at every process step. Then solder masking, legend printing using white inks, scoring and routing, because in some cases the panels may have a large number of boards. So, you have to isolate these boards, and then in some cases in the individual boards you may have to perform some kind of a routing or opening a slot, that is basically for introducing an electromechanical device or a chassis part of it into the board. You can do edge chamfering, typically making the board edges smooth enough. Typically the board edges will be sharp after the manufacturing process is over, but then you can smoothen it out using edge chamfering. Then the board will be done or sent through for electrical testing. In this case it is known as a bare board testing. Here you will do an electrical test that is basically aimed at looking at shorts or open, whether there is a problem in the manufacturing that has resulted in a short or an open. So, these kind of indicators will be given to the manufacturer for every single board. So, you have to qualify every single board for all of these quality inspections, including electrical testing. And finally, the board is packaged according to the recommended packaging material and methodology and then shipped. Now, I mentioned about the plated through hole process sequence. What you will notice is that the board reliability rests on the through hole quality. So, how do I measure the quality of plating and the thickness of the copper plated inside the through hole wall of the printed wiring board? Obviously, you cannot examine every hole. So, you have to prepare some coupons from probably 1 in 10 panels that will give you an indicator of how your plating bath and how your processes work. PWB microsectioning is one such example where you prepare coupons for testing the quality and testing the nature of your plating process, because that is a key to the yield part of it in manufacturing. So, I will take you through this video where we show you how to prepare a sample of a plated through hole, which will be used for analysis and also measuring the copper thickness. Now, basically we will prepare some test coupons using some epoxy material, and then we will zero in on the site where the sample needs to be measured, and then microscopically look at whether there are cracks, whether there is a delamination from the base substrate, and the nature of deposit, whether it is porous or hard, and whether it is having the required thickness. You see in this particular instrument, which is basically a sawing machine, where you can see here the PCB, a small sample which contains the through holes has been clamped, and then you can see here that there is a saw, typically a diamond saw, that is activated, and there is a liquid here, typically water, to remove the heat while the sawing cutting process is on. The board is introduced to the saw. Now, cutting takes place at slow speed because you do not want to damage the sample, and the cutting is now taking place typically at the through hole, okay, right near the through hole. So, you do not want to damage the through hole, you are going to cut this very close to the through hole, and then using polishing methods you are going to approach the site. Here you can see that the technician is introducing the PCB which contains the through holes. You can see the through holes into a template. Now, you can see here this is a template which is now introduced into a container, and here you can see we are now mixing an epoxy material, and on the right you will see a hardener is being used. So, based on the recommendations of the manufacturer, epoxy and its suitable hardener is mixed thoroughly without air bubbles and slowly introduced into the plastic container which contains the printed circuit board coupon. Now, here you have to make sure that you do this process very slowly. Lot of heat will be generated. This is an exothermic reaction, and you have to introduce the epoxy material slowly into the container to make sure that there are no air bubbles. So, typically you can keep the epoxy material to stabilize enough after it is mixed for about 10 to 15 minutes and then introduce into the container. Now, this is a quick set polymeric material. It will set quickly in about an hour. Now, you can see here that the coupon has been completely set. You can now release it from the container. Now, this sample which is there embedded in this epoxy is now, you can see here that the PCB is now embedded into the epoxy coupon. This is called a potting process using an epoxy, and or you can say this is a cross section sample. We are now at the intermediate stage of looking at the site where we want to measure the copper thickness. Now, after this process is over, we now have to polish the sample to get close to the area. We are looking at a few micron thickness. Therefore, the polishing process from that raw coupon has to be very slow. So, here you can see there are various materials used, typically emery paper of various grades that we normally use for polishing, but here we have to go from coarse to less coarser and more fine emery paper material, and you can also use some kind of a slurry alumina silica gel, for example, to aid you in the polishing process. So, this container which contains the paper, emery paper, also holds the sample that we have just prepared, and then using some kind of a slurry, typically water, and you can see here alumina silica gel is now introduced and then continuously polished at very slow rates or at high rates initially, and then slowing down the rate of polishing. Here you can see the surface of the coupon as was done after the coupon was released from the plastic container. Now, after polishing, you will slowly approach the PTH area. You can see here very carefully the two plated through holes and the copper very clearly visible to the naked eye, and you can now introduce it into the various microscopes that you might have and also measure the dia as well as the thickness. So, typically this is a important and a must process in the volume manufacturing also. So, when the drilling process starts for certain panels, they will drill these coupons of various drill sizes, and then the quality team will have to do samples for each of these coupons or earmarked areas, and then they have to report back to the manufacturing line about the quality of the deposit and how much tighter control they have in the deposition rate, because here the electrical performance is going to depend on the thickness of the copper deposit that you are the manufacturer can provide you, because you can't plate too much of thickness of copper more than necessary, and also you can't have lesser thickness other than the specified. So, these videos have given you highlights about the stricter quality control that establishes in today's manufacturing process, which the designer should be aware of. Now, we look at the post process, for example, solder masking on bare copper. It is called SMOBC. Now, you have protected copper with tin, but tin is not a good base for applying solder mask. It can peel off because the surface of tin is very smooth. It does not provide good adhesion. So, typically some people opt for applying solder mask directly onto the bare copper after treating the copper sufficient enough to hold the solder mask. So, what are the steps for SMOBC? Plug all the through holes by either tenting using a dry film process or ink printing using a stencil or a screen printing process. Chemically strip off the tin metal until the copper is exposed. So, this has to be a carefully done removal process, otherwise you will remove the copper also. So, based on the information on the manufacturing line about the thickness of tin that you have coated, you can safely remove the tin plating. Treat the exposed copper to convert to a black or a brown oxide. This is basically a surfacial treatment that you can give to convert the exposed copper on the surface to its oxide, and then you do not have to convert the entire copper. So, once the top atomic layer of copper is converted to its black or brown oxide, different compositions, you can now apply the solder mask using stencil printing or a dry film or a liquid solder mask using curtain coating. Then you cure it using thermal process or UV curing process. After that, you can do the imaging is part of this process, and then you can remove the unwanted solder mask. So, this is how SMOBC is done. Now, the color of the solder mask is generally green, and white legend ink is typically used on this green background, so that there is a very good visibility. There can be other colors, but these are general standards. And the picture on the right shows you how edge chamfering can be done to the edges of the PCB. Now, routing is another process that is done on completed or finished boards. It is a cutting operation used to create channels. You can see in this particular picture, right at the center of the PCB, a particular channel has been cut open. There are no circuit in these areas, but typically these are used for holding some kind of a mechanical device or introducing the PCB in a chassis which contains some kind of a protruding mechanical device and so on. And these are special cutouts introduced basically based on the product design requirement. I talked about bare board testing. On the left, you see here there is a bed of nails, and these are used by all manufacturers as a compulsory test for qualifying every single board. What does this mean? There is a circuit pattern for your board, and that is dominated by your net list. So, based on the nets, they will produce a bed of nails. You can see the long protrusions. These are stainless steel pins or nails that typically depicts your circuit pattern, and this is done on some kind of a plastic mold, typically polycarbonate and so on, and then your board will come and sit on this bed of nails, and based on the through hole coordinates, they will perfectly snug fit into the bed of nails. And then you will now look at the parameters like shorts or opens on your test board by applying a small voltage. You will now activate the board to get some information about which nodes or which part of the nets are open or shorting. So, you can mark those areas, and if this is going to be a consistent or persistent defect, then there is some process defect which can be identified, and the information can be passed on to the particular section in the manufacturing for identifying the defect and rectifying it. So, otherwise some kind of a repair can be done if you have very small defects. For example, it could be a lift off, or it could be some kind of a broken line due to handling, improper handling during the manufacturing process and so on. Now, for assembled boards, what you see here on the right is a picture showing you what a flying probe tester can do for assembled boards. So, in a completed bare board, you have to do a bed of nails test, but in a finished board with components, typically you will use a flying probe tester. So, what is a flying probe tester? Basically, there will be different probes, and there will be the CAD data that will be loaded to this equipment based on the net list. Now, one of the probes can sit on one end of the net, and the different probes can go at the different nodal points of the net and say or tell you which segment is not working or which segment or which segments are perfect, because this is now dominated by the soldering process that you have done. So, this has to be a very slow process, and again there is a hindrance in terms of the components mounted, accessibility is a problem. You can do it simultaneously at both sides of the board, as you can see here. So, you can use different probe points simultaneously to check a particular net and see the failure at different places. So, these are equipments that are used, one on the left at the manufacturing site of the PCB and on the right in the assembly segment. Now, in general, board finishes will be either a solder finish. So, you can expect electroplating of tin to take place, because tin lead and lead is not being used today or not recommended to be used. We expect that solder finish using electroplated tin is an accepted process, or you can have a finish with gold. I mentioned earlier, when you plate gold, you have to plate an undercoat of nickel and then have gold plated on the nickel to prevent gold diffusion into copper. So, today electroless nickel gold is a popular process in many countries, and the thickness is well controlled by electroless nickel gold. So, the board is now ready for assembly at this point of time. Now, we will look into some aspects about multi-layer boards. We have seen so far double sided boards. Multi-layer boards, laminated multi-layer structures are made by stacking separately made layers and pressing them into a mono block in a multi-layer press. So, you can have a double sided board and another double sided board. You can introduce them into a multi-layer press, separate them by a dielectric material called a pre-preg, as you are aware, and then they are pressed in a multi-layer press to get a 4-layer structure and to the required thickness. These are called conventional multi-layer boards, because today you have what is known as a high density multi-layer structure made by sequentially adding layer by layer copper and dielectric onto a existing core substrate. So, this basically leads to what is known as a high density interconnect structure. You are aware of the term high density interconnect structure, where we are typically talking about existing core layer. It can be a 2-layer board, and then you add one layer at the top and maybe another layer at the top, then have a dielectric and another copper layer here. So, you can have 5 layers built by sequentially adding copper and dielectric material. So, the construction of laminated multilayer structures, the key raw materials are, you should have thin core laminates. Typical dimensions could be from 0.5 mm to 1.5 mm. Pre-preg material 0.5 mm or even downwards 200 microns 0.2 mm to 1.4 mm. These are all based on the kind of final dimensions that you require as per your design. Treated copper foil, because as you build the multilayer structures, you are introducing copper foils in some cases, or you can also add copper by plating. So, typical thicknesses are from 10 to 35 microns. Again, these are dependent on the electrical design specifications. The manufacturing options will be, first, copper foils will be bonded with a pre-preg material. So, this is the conductor and here you have the insulator. These will be introduced into the multilayer press along with the core, and then structures can be layers can be increased. The second point is using rigid laminates bonded with a pre-preg material. Okay. So, we are going to see both of these options. So, in this second case, rigid laminates, let us say a 4-layer board is now introduced with 2 pre-preg layers, one on top at the bottom, and then you can have copper foil on both sides to get a 6-layer board. Let us look at a case study or an example for a 4-layer multi-layer board construction. The option 1, the first thing here is stack bonding 2 double-sided boards using a pre-preg material. Now, assume that you have done this part. This is a double-sided board. You can see here there is copper, you can see here there is copper, and this is a two-sided printed wiring board. Similarly, here this is a two-sided printed wiring board, which you have done as per the process that we have just described. Okay, this is the copper, here you have the copper. Now, the design has been in such a way that if you introduce these two layer boards together using a set of pre-preg materials, here in this particular example I have shown you there are two pre-preg sheets. The thickness can be varying from 200 microns to let us say 500 microns for each of these. Introduce them and then stack them together and send it to a multi-layer press. Now, the boards will become the epoxy will melt and then they will nicely sandwich between the two double sided boards. Later, you can now introduce a through hole from the top to the bottom to let us say interconnect layer 1 to layer 4. We can also build copper on one side by adding the dielectric material, or you can do the imaging process at the top layer and the bottom layer subsequently after the drilling process is over. So, for example, if you want to interconnect layer 1 to layer 4, you can drill a through hole and then you can make it conductive, and you can access from here to here by using a plated through hole process sequence. So, these are the design variations which can be very clearly explained for the manufacturer as to what you require. The second option is that you can do a stack bonding of a double sided board and adding copper foil for the final two layers. So, in the first case all your imaging is complete, and now here we are talking about a double sided board. In this particular case, a double sided board with the copper and the dielectric material. Imaging is complete. Now, we are introducing the pre-preg material here, and then this is the copper foil, again another copper foil. It is now sent to a multi-layer press. So, at the required or specified temperature and pressures, there is good bonding. Now, you can again introduce a through hole. You can do imaging here, image your copper areas at the top and the bottom, and then establish connection between layer 3 and 4 in this case as notified. So, here again you will do a dry film process, you can do a pattern plating if you require. It depends on what kind of copper foil thickness you are taking, typically it will be very thin. Then you can add enough copper to create your required copper thickness top and bottom. You can also establish connection between the layer 1 to the inner layer of copper. Here again you can do that and you can make it conductive. This whole wall can also be made conductive. So, this is a through hole. This is typically a blind via. This is again a blind via, and here you may probably have through holes which will now become a buried via. So, these are the various schemes. So, in a nutshell, what are the major steps in creating a 4-layer board? Process a double sided board or let us say 0.8 mm core. Your starting double sided board will be 0.8 mm. Now, you lay a 0.4 mm thick pre-peg on either side, right. So, it is almost 1.6 mm thickness now. Then you add 35 microns of copper on top of the pre-preg on either side. So, that completes the copper construction. Introduce it into a lamination press, specified pressure and temperature. It is a very slow process. Now, cool it to room temperature, drill the required via holes to connect the top and the bottom. Then plate the through holes through the sequences that I mentioned earlier, pattern plate top and bottom, and then post finish using tin or you can use nickel gold. Then it goes for solder mask, then it goes for legend printing. So, this is the kind of steps that you will look at as a designer, how your 4-layer board is going to be manufactured. So, having seen the basics about double sided board and multi-layer boards, we will now slowly get into the topic of high density interconnects. The interconnect hole formation, as you have seen here, basically is by through hole, buried or blind vias. They are typically done by mechanical drilling, but here in mechanical drilling there are certain limitations. What are the limitations? They are basically the size of the drill bit, the size of the via that you can drill. Today's modern equipment can drill very safely, let us say up to 0.3 mm or 300 micron, but below that, let us say if you want to do 0.2 mm, 200 microns, it is expensive because the drill bit is expensive. The equipment also becomes expensive because of the high RPM that you have to use for lower drill bit sizes. But today we have mechanical drill equipments that can drill up to 0.125 mm, 125 microns. So, lot of quality control needs to be there, especially if you want to plate a through hole which is having a high depth. When you are using lower drill sizes, you have to make sure that the thickness is small, so that you can maintain the aspect ratio. The other options today that is available for building high density interconnects is to use laser drilling and do away with mechanical drilling. What are the lasers that you can use? You can use carbon dioxide laser or YAG. YAG stands for yttrium aluminum garnet. So, basically you are going to use excimer laser, or you are going to ablate or burn away the material in order to produce a hole. So, if there is a substrate, you are going to burn away this material here and then remove the dielectric material, so that you get the hole. Now, the process looks simple on description, but again we are talking about the quality of the hole that is required if you are going to use laser drilling for a through hole with a moderate aspect ratio, and then follows the adaptability or the conditions of the hole wall for subsequent electrolysis plating. Because if you drill a hole wall which has got a lot of debris and defects, then it is going to be reflected in your electrolysis copper plating. Therefore, one has to be careful about what kind of methodology you are going to use. But laser drilling equipments are becoming very common, they are affordable, and they have indicated that you are going to get a very high throughput and yield in terms of number of PCBs produced using these laser drilling machines. The other step is using a photochemical via, where we use a liquid photo definable dielectric layer, and you are going to use photolithography to open up the via from this very thin dielectric layer material. So, it can be either a liquid or a dry film, but the dry film photo definable dielectric layer is not available in abundance. So, most people tend to use liquid dielectric layer material to produce photo definable micro vias. So, when you use these kind of methods other than mechanical drilling, we are talking about producing micro vias, not the vias that we normally use for component mounting, which is plated with copper. So, micro vias by definition is typically those vias which have dimensions of 150 micron and less. Today it is redefined as 125 microns and less. So, the methodology for micro vias can either be laser drilling or photochemical via formation. There is another method called wet etching, but it is not it does not produce the kind of results that we expect for these kind of high density interconnect structures. plasma, using a dry plasma etch has been tried in prototyping. It produces better results in terms of the whole wall definition and the kind of undercut. When you talk about etching, there is always a problem with undercut, and wet etching produces high undercut compared to a dry plasma etch, but it is a very slow process. We look at the different interconnect hole formations from these figures. The photovia formation happens this way. As you can look at this picture on the right here, you can see that there is a photo imageable dielectric layer that is coated on an already existing core substrate. You can see the yellow lines, that is the photo imageable dielectric material that is coated. It tends the through hole, and it also covers the non-circuit areas on the board. The red areas are the copper patterns that have been established already. In the second step, you can see that an imaging process is carried out, a photo patterning process is done. If you can show this picture clearly, completely, that the microvias are generated here. The microvias are generated here by a photolithography process. Now, the next step is doing electrolysis copper plating process. Now, you can see here a thin layer of copper has been formed using electrolysis copper. It covers the entire depth of the microvia. So, the microvia becomes conductive, and it also contacts the layer below. So, this microvia after electrolysis becomes completely conductive, touching the base copper immediately below the dielectric material. So, then you can add the required amount of copper that you require by following it up with a electroplating process. So, the thickness is increased. Now, you can do further an imaging process. Okay, you can do another imaging process, and then you do a print and etch and then define the tracks and the pads. So, you can repeat this process a number of times to get the number of layers. So, this is the essence of a photovia formation. This can be done at the top of the copper or top of the printed circuit board core, and also it can be done at the bottom. You can do it separately or simultaneously. The only thing is that there should be very good registration between the microvias and the through holes or the patterns and the pads that you have defined. So, you have to generate masks for each of these layers. On the left, if you see, we are going to now talk about laser drilling and how you can use laser drilling for sequential build-up circuitry. So, you have a base core that is already generated, and you are adding a laminate RCC, that is resin coated copper foil. You can see here this is introduced, and then there is a lamination process that is done. So, the dielectric will ooze out upon the temperature and pressure that is applied. Now, you can drill on top of the copper and the dielectric using UV YAG laser, yttrium aluminum garnet. It is basically an ablation. It removes the copper and it removes the dielectric material. So, you can see here the opening has been created. Now, you can do the copper addition by pattern plating by applying a resist or a photomask. So, you can see that the microvia has been plated here, and then you can define the pattern by subsequent etching process and defining the tracks and the pads. So, this can be done for the bottom side also, and this is a similar process compared to a photovia process. Only difference is that here you use a laser source, and you can get very good definition using laser drilling process. On the top, you see here the plasma etch to create a microvia and how it is suitable for SBU process. Now, you have a base core here, inner layer pattern you can see, and there is a non reinforced resin dielectric material. Then you create a window by etching and then introduce the plasma etching. So, basically the plasma is generated in a chamber where, for example, you have two gases, let us say CF4 and oxygen interacting together, and you get a plasma from the resultant free radicals or ions at higher frequencies. Now, these resulting ions or free radicals will react with the dielectric material, and basically it is a slow process, but you can see here the material is ablating, the dielectric material is removed here, you can see in this particular figure, and then the copper etching is done basically to remove the kind of protrusion that you can see here that the plasma etch has not taken care of. Now, you can do a very quick copper etch and then you get a perfect hole wall, and this is finally converted into a interconnect by plating. You can do electroless plating followed by an electroplating to get a well defined hole wall. So, this is a very good description about plasma etch and how plasma can be used. This is a dry plasma etch process to create a microvia, and following the creation of the microvia, it goes into the layer formation by addition of electroless copper and electroplating copper. So, the summary here is the interconnect hole formation for high density interconnects can be done by mechanical drilling in one case, but for vias which have a smaller diameter, people are going in for laser drilling process, plasma etch and photo via formation. As I said before, mechanical drilling to the extent of 125 microns is currently available, although expensive, and if you include that, these are the 4 major methods to create a microvia. The basic reason is that mechanical drilling has its own limitations, because the minimum hole dia you can create is 0.15, registration is a problem, and debris and smear generation during drilling can block the holes. You need proper hole wall preparation before electroless plating. The economical aspects, it has got low yield because you are going to depend on sequential drilling process and it can take time. Whereas the processes like laser drilling and photovia formation especially is a parallel process. Although laser drilling is a sequential process, photovia formation can be very economical and it can increase the yield because it is a parallel process. High investment is required for multi-spindle drilling machines. Drill bits are expensive. You have to use entry and exit foils. Deburring and desmearing is a very important operation to remove the debris and to prepare the hole wall conducive for electroless plating. And the maximum RPM obtainable with conventional spindles has prevented the smallest diameter drill bits from operating at their most efficient cutting speeds, which results in breakage of drill bits and so on. So, we will now look at in the next class a comparison of all of these various methods to create microvias and look at how actually you build high density interconnect structures from a given core substrate.